So this paper is a very big abstract summary or a kind of like a history research paper of all the research papers that were important and were published between the between the timeline of 2023 to 2025. Okay, so this is like a movie is like a movie. This is like a trailer for the movie, and the movie is reading all that research papers. So this is like a trailer for that. Okay, and CPVR, ICLR, and NEUR, IPS. You can see those things. So these are nothing but conventions. These are conferences actually. CPVR stands for Conference on Computer Vision and Pattern Recognition. ICLR stands for, this is also a very big conference that is like International Conference on Learning Representations. Those people who are in data science and artificial intelligence branch next, and those people who were in third year and were in second year and have this course called representational learning and all that. So this is related to that, and this is like very, this conference relies is like specializes heavily in deep learning architectures and all that. And then NEUR IPS. Any guesses? NEUR, of course, stands for neural, and IPS stands for information processing systems. So this is like a very big, this is again a very big AI conference, and all these conferences had these papers were presented there, and these 26,000 paper which were accumulated only in the span of like 2 to 3 years, 2022 to 2025 and all that. So NEUR IPS stands for like Neural Information Processing System, and it's like their topic is like deep neural networks and neuroscience and statistics and all that related stuff they do. Okay, yeah. So in this we will be like going through I in like how the today's modern world, okay, today's modern AI, what is the AI bubble today, how it has been like concentrated towards large language models only. Large language models these days, VLMs have come. We will be discussing VLMs as well. How like all of the like most of the biggest part of today's artificial intelligence is now LLMs only. Like whichever big AI company that we see, there what is the biggest product? There's it's always an LLM only, right? We see Anthropic, we see Gemini, we see ChatGPT and Grok even. These are one of the biggest AI companies, and all of them have, I mean, like they focus only on large language models and all that. And they do have other products as well. But that is like where they have all concentrated in now. Okay. So, yeah. Introduction. So like this, in this, like what is being told is like, uh, now everyone feels like AI research has completely changed, but like nobody has proven it with numbers yet. We in this research paper we will be learning through numbers how AI research has changed. Okay, here you can see there are some uh, you know uh, these short forms: CLIP, BLIP, LLAVA, and all that. So what are these? I'll tell you that. First of all, the full forms. CLIP stands for Contrastive Language Image Pre-training. So what is this? This is an architecture that trains an image encoder and a text encoder simultaneously. Okay, and this uses a laws to map. This uses loss functions. Okay, to model these two text encoder and image encoder simultaneously. Okay, so CLIP stands for that. Then is BLIP, bootstrapping language image pre-training. BLIP here, it stands for bootstrapping language image pre-training. So this is like a flexible framework. This is capable of switching operation modes to handle both visual understanding and visual generation. Like you put an image and then you say, for this image, give me a very good caption. I want to post this on Instagram or LinkedIn. So how will that happen? This will happen because of BLIP. Okay. And the CLIP stands for, like, it acts as a eyes for the artificial intelligence today. Then comes LLAVA, Lava, which is large language and vision assistant. This is these days many we see the shift has been through the shift has mean like from to a single perspective model, like earlier in like 10-20 years ago, AI was not present. But 10 years ago, when AI was just starting out, people used to make specific AI models. Like, I will make an AI model just to, detect potholes. That was done like 10 years ago. But these days, we need multimodal systems. We need an AI that can, detect a car, detect do multimodal classification, which can be used in like self-driving cars, which can detect potholes, which can detect dogs, people walking outside, which can detect the road and the pavement, which can detect cars. And Java is a model that bridges a LM via simple projection layer. So the meaning of this is that, okay, yeah, I got a text, that's why I stopped. Yeah. Uh, okay. So this is like a multimodal system, multimodal AI, eyes of AI. These have emerged in the field of artificial intelligence over the year, from 2023 to 2005. What all things that have come up, and what is the current thing that is trending, and what you should be learning. Okay. So, reading this paper, which is an analysis of all the research paper, you might get a idea of what to continue in the future. Okay, so this part is macro trends, in which some trends are listed here. Okay, active learning, meta learning, 3D detection and segmentation, and language slash multimodal slash LLM. So here we can see that this contains the most critical statistics of this paper. Okay, this chart is. So if you remember only one thing after, okay, yeah, did you guys see that notification? Were you guys able to see that notification? Okay, okay. So where were we? Yeah, we were here. So here you can see that vision language model and this large language model and multimodal are the things that are trending here. I will read some part of this, which is important. The consolidated view highlights three macro patterns. One is a sharp takeoff of uh, LLMs and VLMs, and then sustained growth of generative model. You can see here somewhere in the generative models are present. Yeah, somewhere here there are. But yes, after that, there is another thing that they have stated, that steady increase of video understanding and stable but controlled 3D reconstruction trajectories. You can see here 3D geometry and uh, segmentation. These things will be discussed in the later part of this research paper, and it will tell that why these topics, 3D geometry and the segmentation, also rose along with these things, because these things have importance in today's use case of vision language models and all that. Okay. Yeah. Next on, we have so many graphs here, which are independent analysis of how things are going on. Okay, these are like all the trends have their own graph shown here, how they grew over there. You can see vision language model grew steadily, diffusion and generative models, then Gaussian splatting and neural rendering. You can see this 3D, as I said, 3D geometry and neural rendering. Things like rendering and image generation and something kind of stuff are also growing as along with VLM. We will see the relation with the VLM in the coming part of this research paper. Okay. Yeah. So with this, I would also love to highlight the decline of some. Yeah, here we can see time series and sequential SSMs. These Bayesian and probabilistic modeling. We can see there is a decline in that. That decline tells us that the shift is now from specific models, like these models do a specific task. These are not multimodal stuff. They cannot do a lot of things. Today, at this present of time, we can see there is a boom of ChatGPT. Why is that? Because ChatGPT was trained on a very large data set, and it is a single model that can summarize things for us, can generate text for us. It can also correct our text. Okay. So there is a single model only which is capable of so many things. So there is the shift has gone from a single purpose to multi-purpose thing. They have faced declines because these are used only for single purpose thing. Yep. Yeah. Then we will move on. These are all of these things are written here only. I will not go into very much depth of that. Uh, then then comes this. Across CPVRs, NUR, IPS, CLR, I have given the full form of these, which are, I will repeat again. So CPVR, NEUR, IPS. CPVR stands for Conference on Computer Vision and Pattern Recognition. Newer IPS stands for Neural Information Processing System. ICLR stands for International Conference on Learning Representation. So these are conferences, okay, and these papers are taken from these conferences only. So VLM abstracts pivot from grounding referring towards instruction following and reasoning, and parameter efficient adaptation, which is like these you can consider it like optimization models or optimization techniques that we used in our classic machine learning. This is something like that. Training is dominated by pre-train plus fine-tune. Now this is something that on which I would love to focus on. I could not highlight it right now, but yeah, with a clear rise in instruction tuning. What does that mean? So you can see that in today's time, when we go to hackathons, their problem statements are such as make a RAG, okay, or fine tune an LLM. No, so what are we doing? We are using a pre-trained LLM and then fine-tuning our purpose on it. Okay, fine-tuning the pre-trained model so as it can work for us. It can work for our purpose. Okay, so that is where this is what this is telling about. Okay, so nowadays people are, instead of training their own model from the scratch, from they are doing fine tuning. Have you heard about AlexNet? So AlexNet was a pre-trained on, I mean, like, it was a advanced version of ImageNet only. It had the data set of ImageNet as well, along with others as well. So yeah, so on the existing stack you built on it. That is what this is telling about. Then then this topic, which is 4.1 models, I would give some clarity on this. So there are various names you can see here: Align, Lava, VLMs, MOE. Okay, we have to go in depth of it. Okay, a little bit depth on it, which is given here. I will be covering them, and one by one we will understand what this means and all that. Okay, so first is Align methodology. Here it is, align methodology. So what is align methodology is that uh, align model functions by scale. I have to go up again, just a minute. Yeah, align model scales contrastive dual conductor, a dual encoder pertaining to over 1 billion noisy image, uh, all text pairs deliberately avoiding heavy curation and showing that scale can compensate for label noise. A vision encoder and a text encoder are trained with a contrastive objective to align representations in a shared space, enabling strong zero-shot classification and cross-model retrieval without specific heads. So if you guys understood this text, then I think you should head to PhD in artificial intelligence in some American university, but I did not understood this part on the first go. So I had to find a simpler definition of it, which I have found it for you. So this means that the align methodology is that to do not waste time cleaning your training data perfectly. This is align methodology. Things on the models that are in this methodology, they're like you give a very big dump of a big large data set to them. Okay, and these models, they do not need you to perfectly clean all these things. They will do that by themselves. Okay, so it's just like a massive volume of data set you have to give it to, and the model will filter out the noise on its own and find what is good for it and work on it. So that is align. We will compare align, CLIP, and blip and flamingo. But let's just first understand what this means. Okay. Yeah. Where was I? Here. Now the next part is clip. So I will read again. Learns image text alignment using a dual encoder. Okay. Trained with InfoNCE style contrastive loss on hundreds of millions of web pairs, producing a universal embedding space for zero shot recognition and robust transfer. Clip commonly serves as a frozen version encoder in a later LVLMs. So also did not understand it. So here is the simple definition of clip. So clip is like main focus of clip. Okay, is instead is that so me like uh, how to say it um so clip is like images into a universal joint embedding space. We can see here joint embedding space, producing a joint embedding space for zero shot recognition. uh, the loss actively rewards correct image text pairs for aligning closely while penalizing mismatch pairs. So in this you can understand like you have Instagram, right? So in Instagram, if people wrote a text that is around the image that they have posted, so this model will do it that how close is that caption to that image, then it is a reward. And if it's not, then it gives a penalty to the I mean like loss function works on that, right? So loss function has to work on that way. You can see like if the model is doing good, then it has to grade it like okay, you're doing good. If it's not, then it has to penalize it severely. So it if the text is like very far away from the image, then it does that. It rates us very badly. So that is clip. Then comes blip. So blip is, I will teach the readers again. Bootstrapping language image pre-training. Introduce a multimodal mixture of encoder decoder that act as unimodal encoder for ITC and image grounded text encoder for ITM and an image grounded text decoder for language modeling. Jointly optimizing ITC, ITM, and LM to support both understanding and generation. I did not understand any of that. So here's a easier definition of that. So Blib is very versatile. It is a single architecture that can handle both understanding and generation. What understanding the image and generation of the text that is close to it. Okay, that is the blip. And it does all of that while also cleaning its own data set as it trains. So here also you gave a very big dump of data set. Okay, so it will clean its own data set, use it, and generate as well as understand and generate both. Does both things. Okay, it does both of that. Yeah. Then comes our flamingo. Yeah. So Flamingo approach, I will read it again, is an LVLM that conditions a large decoder-only LLM on visual evidence via gated cross-attention layer. A lightweight perceiver resembler compresses image video features into a small set of tokens fed into large language models, enabling few-shot multimodal learning on interleaved image text streams. The work highlights training on a mixture of web corpora with interleaved modalities. Did you understand it? I did not. So here's a different interpretation which is simpler to understand. So Flamingo approach keeps a massive language model intact, but it weaves visual attention layer into it. Okay, a large language model is there, and Flamingo puts a visual attention layer into it. More, this is like more integrated approach than Clip's separate independent versions. What is Clip doing? Here there is a one model that is understanding, there is a one that is mean like generating the text, and there is a one that is comparing, okay, how far it, how close it is. You guys know, right, how encoder decoders work, right? So that is how they work it. But the flamingo is like the attention layer for visual attention layer is weaved into the same language model. It is just like Clip, but uh, uh, encoders and I mean like the perceiver and resampler compresses image features into a small set of tokens fed into large language model. Okay, just understand this part. Okay, that's it. Then we can see here how their trends goes. Top models referenced by VLM papers. Our lines were like 4.3%, then it grew 5.8%, then it decreased in 2025. Here we can see we should focus on this, which we will be learning in future. It grows, it grew in 2025, whereas blip, it we can see blip has like a very big like it has seen a downward trend. Then again Clip actually saw increasing trend, but it's nowhere close to align. So if you understand align, then I think it will be like really important for you. Then we can see flamenco has like disappeared. Okay, so yeah, understand align. I will repeat align again for you. What is align? In align methodology, it was like it is very efficient. Like you give a very big dump of data set to it, and it will use what it has to, and it will like do everything on its own. You don't have to give a clean data set to align models. That's that. Then comes lava. Okay, lava's okay. Lava is also I will read it again. Large language and vision assistant. shows that visual instruction tuning supervising an LLM with high quality GPT-4 generated multimodal conversation paired with images can endure a model with broad instruction following, reasoning, and perception skill. A simple projection bridge gaps image features from clip-like encoder into an LLM token space, after which stage-wise tuning on the synthetic conversation yields strong zero-shot generalization. You want an easier approach of that? So here's that. Lava's recipe is shockingly simple compared to Flamingo. What it has to do is just train small translator layer. It has to just do some part of it correctly. Okay, turn an image into text token and let a clean data set do the heavy part of it. Okay, so what it will do is like for a small part of it will do, and then a clean data set will do the other part of it. This is like very simple, and other models were like very a little bit of complex to implement, but this is a simpler approach, and we can see here it has a growth because it has a simpler approach. So in today's world, we can see simplicity is winning over complexity. Then comes Dino. Here we can see that Dino has also seen a rise. So it is important that we discuss Dino. So I will read again. Dino demonstrates that self-distillation without label, student-teacher with momentum, applied to vision transformer yields emergent patch-level correspondence and high-quality features for downstream tasks. Key ingredients are multi-crop augmentation and centering strategies that stabilize training. Dino is often used as an initialization or back in vision system. Sorry. Dino V2 scales this recipe substantially. It trains larger VIT backbones on a carefully curated, deduplicated image corpus, strengthens the teacher-student alignment. So, how many of you are learning reinforcement learning? Can I see that in chat? Like, how many of you have like I mean, like gone through reinforcement learning on your own? Okay, so I guess nobody's listening to me, but it's okay. I'll still stay because it's recording, so I will give a smaller definition of this. Dino merges traditional object detection systems with open vocabulary pre-training by directly aligning specific region level visual characteristics with free-form language strings. It allows a single detection pipeline to easily locate both pre-trained traditional object categories and arbitrary text spaces. This model is what makes open vocabulary detection work. Instead of old systems that can only find a fixed list of items, this system can locate a specific description, the red mug next to the laptop on command. So, sorry. Dino makes that possible. Okay, it's like so it in I gave that example of dictionary, right? If you listen to me, that this model is like open book vocabulary detection makes what open vocabulary detection work. Okay, in the older system, you have to find a fixed item, but in because of Dino, it is not possible that in an image, if you say Chat GPT to remove, there is a man behind me standing, remove that. It is possible because of Dino only. Okay, these days. Now we should focus on this part. This is like written like in a very much detail here. I will read this part. Cross attention or simple projector. No, this does not start from here. In table 2, dual encoder families, align and clip, emphasize dataset scale and a contrastive recipe for broad transfer. LVLM families like Flamingo and Lava inject vision into a powerful language decoder via cross attention or a simple projector layer, and then rely on instructions like supervision to elicit reasoning grounding. Blip occupies the middle ground for unifying ITC, ITM, LM, and bootstrapping cleaner captions. Dino and grounding Dino secure the vision side self-supervised feature and open vocabulary localization that downstream LVLMs frequently built upon. Finally, MOE provides a path to scale language backbones with sparse compute increasingly common in recent LVLM. So if you remember this part, then a lot of part that we discussed above will get covered. Okay, we need to focus on this part now that Align and Lava is something that is growing. So you can make a project regarding that. And this is also very important. We can see multimodal LLMs, which are good and are growing. 2021, 2022, I will not look into that. I will look into the data from 2024. Here we can see uh, this Quen. We can see Quen are like very trending these days. Quen 2.5 VL, Quen 3 VL, Lava Open Vision. This is not a Quen. Quen Omni. If you guys have used this, then yeah, you would know. Yeah. So I would encourage you guys to make a small project on these stuff, just like a POC. You can do it using cursor or anti-gravity, whatever. But I think implementation would be a good thing to do. Okay. This way you can add that into your GitHub account and it might look good. Okay. You can work on this part, just a simple project in order to understand how this you know how these encoder decoder and all the things that we understood about cross attention thing, how like in a in an LLM you make an another layer for vision part so that it can work as a VLM. That part you can do. Okay, I believe that you would have made an simple encoder decoder thing. So if you have not, then I will tell you a little bit about encoder decoders. So encoder decoder concept is that we learned in image generation part and image generation part is what we look into this. I mean like in that part it comes the so what it does is that in in image generation there are various different kinds of models that are present. So one model that can be used is that you can make a model. Guys, can you give me a second? I really need a second. I'm getting an international call. Sorry guys, I had a I had to leave. Okay. We'll do that together. I'll tell you what all parts that I have messed up, and we can cut those past parts and then reach. Okay. I'll go back again to this. We are almost halfway done to this, and I think, the most important takeaway of this paper was only these understanding these methodologies, and I guess we have done that. Now it's just like smooth as butter. So we'll go through that. Yeah, give me a second. Okay, so now we are in the part of fusion or architectural integration part. Okay, I'll read it through my text. Okay, so the authors here have presented data tracking how researchers physically wire vision and language layers together inside the neural network architecture. Okay, uh, here we can see there are three, uh, three paragraphs. In these three paragraphs, and we will explore the shifting hardware design philosophies of modern multimodal AI. Okay, first is we will discuss in this part. Okay, uh, prompt and prefix tuning stand out as most widely used fusion mechanics in the literature, climbing consistently. Okay, here we can see that uh, this part is not well. Uh, where was that? Okay, I'll tell you. The lightest incredation methods, like the integration methods, which are like very simple to do, are winning. As we saw in this part, Align and Lava are like very growing. Okay, that was one takeaway. Then the other takeaway was that uh, an efficiency fine-tuning method that keeps base model weights frozen and injects a small low-rank matrices into a tension layer, drastically reducing the memory and computational footprint required for specialization. So here we can see LoRa. Where is LoRa? Which is low-rank adaptation. LoRa, where are you? I'm not able to see it, but it's okay. Then we'll move on to this part that is task. Uh, the data profiles a clear evolution in what task models are actually being assigned to solve between 2023 and 2025. There is a decisive, sweeping pivot towards complex multi-step reasoning, alongside a broad coding of legacy localized perception tasks. Multi-step reasoning and instruction following represent the fastest growing task category in the entire study, spiking from 13.5% to 25%. The massive surge is driven by instruction-tuned systems that attach visual adapters to frozen language decoders and train them on open-ended conversational soups. Okay. Then is the motion of grounding, which is present here. Object grounding are referring tasks which once dominated the VLM landscape, served a sharp contraction. Open vocabulary detectors remain vital infrastructure, but they are no longer positioned as the primary highlight of research papers. Then we'll move on to training paradigms. Training paradigms. First table talks about adaptation rules. The text tells us about a clean transition towards fine-tuning strong existing pre-trained components using parameter-efficient optimization tasks and curated instruction data. In contrast, designing web-scale weak supervision from scratch plays a much smaller role in new publications. Then pre-train plus fine-tune. Umbrella remains the standard recipe for the field. This is like significantly still in the market, growing by 5.2 percent points. The layout relies on taking a frozen visual encoder, pairing it with frozen LLM, and tuning only the modular bridge layer. Prompt vectors. Uh, Prompt and prefix tuning rose by 1.3 percent points, emphasizing the trend of optimization via continuous vector adjustment rather than updating deep structural weight parameters. LoRa and instruction tuning is also written in this part, which is LoRa, as I said, LoRa and adapters expanded steadily, driven by their minimal VRAM overhead and exceptional optimization stability when combining multiple skills. While talking about these things, I will also talk about quantization of models. So these days, do you know, guys, the reason why we are not able to run 8 billion parameter model? Quen has made 8 billion parameter models and 40 billion parameter models as well. Why are we not able to run it? Suppose we have a 16 GB space on our laptop, okay? 16 GB is a lot, and it is enough to run a 8 billion parameter model, but we still don't do it. The reason is because of the quantization of the model. Okay, so you have heard about floating point 16, floating point 8, floating point 32, and all that. 8, 16, 32. So what are these? These are the quantization of models. What are these? I will tell you in detail. Suppose lower the number, that is 8 floating point. So you can understand that the entire thing is broken down into very small 8 floating point numbers, because computer is going to understand everything in numbers. If you give it an image, it will convert into number. It will give, if you give it a text, it will convert into number. If you give it a speech, it will convert it to number. It has to understand everything in numbers. So floating point 8. So imagine how many numbers uh, it makes if you set the quantization to very small. Okay, you have to consider the VRAM, virtual RAM, that you have in your system while doing that. That is where if you keep it is considered like it is good to keep the VRAM to 816, but it depends on your system as well, whether it does has that kind of VRAM also or not. If it is not having that kind of VRAM, virtual memory, or RAM, then it will not be able to support that kind of a model, and it will perform very badly. Okay, while you know AI engineers have to think about this stuff when they have to deploy the models. They are not the ones that are making the models. You are the one. You will be the one. Machine learning or ML engineers, or what all people are there. I don't know. I don't even know. Data scientists and all that. They are making models. You will not be thinking about it. You made an API of that, but AI engineers who will be deploying it, they will have to think about, okay, we have to use this model. What will be the most efficient way of using this model? Most of the good models run. I mean, like companies, companies have so many choices. They can buy a good server and they can host the model there, and so the floating point can be kept to like 8 or 16, and the model will work wonderful. But when you are doing it, suppose your company is very poor, you don't have a good server, then what will you do? In that case, you will have to use a floating point 30. Along with that, you would have to use other models as well to help the model. Okay, we cannot entirely rely on that model alone. So that is something that you can understand or learn more about. Quantization of models, this is a new thing which I understood while doing my internship. You can also explore this part. Yeah, so yeah, now we'll move towards lost families. This part is that you can see here. I guess you might have heard about this word called cross entropy, right? Yeah. So let's wrap this up very quickly, and I will let you guys go. I will read this part as soon as possible for you guys. Uh, First is resampling, rebalancing, and grading rubric. The exact mathematical loss functions reported in abstract noting a distant were used, noting a distant rebalancing away from retaining focused objectives towards alignment and distillation formulas. Then contrastive loss retreat. Contrastive loss retreat. Where it is contrastive. Mm, okay. Yeah. Contrastive objectives fell by 5.7 percentage points. Okay, they fell, reflecting the pivot away from building text image models from scratch. Then info INC, information noise contrastive estimation. What is it? A contrastive loss function used to maximize the mathematical similarity between positive text image pairs while minimizing similarity for negative pairs. These are supporting loss functions which are used in the paper. I will just name them. One contrastive info NCE already discussed. KL distillation, triplet ranking, cross entropy, MSE. Already, everyone knows about this. Dice, Charmer, EMD, and all that. Data set now. Ah, okay, finally we are coming to the end of this research paper. The dataset reporting gap. The authors introduce their dataset tracking findings, warning upfront their paper abstract systematically underreport explicit training sets. This is especially due to modern generalist models, which often rely on massive probability or heavily filtered corporate data mixtures. A warning before what is this? It is a warning before reviewing the metrics. These data set citations numbers are conservative undercounts because papers rarely list their exact raw data sources directly in the abstract. Okay. This part is nothing but is just telling how reliable this paper is. Then comes modalities, co-mentions with VLMs. What were things that were co-mentioned with VLMs? I will just 3D point, image text, depth, audio speech, video text. These were the things that were also mentioned in the VLM papers. Then cross-running comparison and practical advice. What is the practical advice that you can keep? Every conference has a clear focus. CVPR is visual and 3D heavy. ICLR is language model heavy, and newer IP is catching up rapidly on VLM application. This is like the crux of it. Every three conferences, one CPVR is a visual and 3D. ICLR is doing language model things. Newer IPS is doing VLM applications. That was it. So at the end of it, I will say that there is no point of reading the citations and all that. The main part that I will say that you can work on right now after leaving this would be to focus on learning of what is quantization of models first thing. After that, you can focus on what were the different frameworks that we discussed: Blip, Clip, LoRa, and this Align methodology, which was running very quickly. I'll give a very quick definition of Align. Again, Align is like you give a very big, massive data set to it, and the model does all the work on its own. So you don't have to do anything on me, like really. So in today's modern world, you can see that models that are easy to apply, which are flexible, they are running the space. So if you will work on that, then it might be good for you. Okay. And any questions for me, anyone? Any questions? If not, then we can end the session. You guys can leave the session. Thank you, Shreya. Thank you so much. Next time you will be do it. Thank you, Divyansha. Mayank, Harsh, you can leave because I have a meeting in like 4 minutes. I have to go as well. I will leave once you guys leave. So, thank you for attending. Thank you.